Hi, welcome back to Math 125. This week we'll talk about chance variability. We'll cover chapter 17 from our textbook. Okay, so here's kind of a sample problem. Suppose you have a box of the following numbers, 1115, and we want to pick out 100 tickets from this box with replacement. And the question is how large should this sum be if I was to add up all of the tickets. And so one way to think about this is that if we pick out 100 tickets from this box, we have a 75% chance of getting a 1, 25% chance of getting a 5. So that means that if I take out 100 tickets, 25 of them should be 5, and then 75 of them should be 1s. If I multiply 25 by 5 plus 75 times 1, you get 200. So this is adding up all of those tickets. So 200 should be the expected value that we get from picking 100 tickets from this box. So let's see if we can find a nice formula for the expected value. So if we want to find the expected value of a sum of draw from a box that we pick out randomly with replacement, then the formula is to find the number of draws that we want times by the average of the box. And so for the previous example, the average of the box is add up all the numbers, divide by 4, which is 2. And because we're picking out 100 tickets, 2 times 100 is 200. So now we'll do this problem. Suppose we play a game at Vegas where we bet $1 on a single number, and if we win, we get $1. If we win, we win $2, and we lose that $1. And suppose that there's a 1 in 4 chance of winning. The question is, how much do you expect to win or lose if we play this game 100 times? Well, the key is to kind of find the box model. That's what we talked about in the last lecture, in the last week's work. So, because we have a 1 in 4 chance of winning, that means one of the 4 tickets is a 2. And then the other 3 tickets, because we win $2 for a game that we win. And then the other 3 tickets should be -1 each, because if we lose $1. So again, having a box model is nice because it kind of simplified the problem into a nice simple box model. And so we use the formula to find the expected value, which is find the average of the box, add together, divide by 4, give you -0.25. That means that on average, every game we play, we lose 25 cents. If you play this game 100 times, then we'll lose around $25 or so. And then, if, for example, if you play 1,000 times, then you lose about $250, etc. What if we pick the 25 tickets from this box? Again, to find the expected value, we use the formula. The number of draws is 25. The average of the box is 3. So we should expect to get a sum of 75. But of course, when we actually do the experiment, we might not always get 75 each time. There might be a chance error. And so, so here's the formula. The sum of the tickets is equal to the expected value. We expect to get about 75 plus some chance error. And so, for example, this chance error could be a positive or negative. Say our sum was 70, because 70 is 5 less than our expected value of 75. Our error is -5, etc. And then the question we want to know is, how big is this chance error? And is the chance error going to be big or small? And to find that, we got to find something called the standard error, or the SE. So the standard error allows us to measure how big this chance error is, and so this is very useful. I mean, as we see later, when we talk about things like polling and voting, of course we can't poll everybody, and so we have to kind of randomly ask some people to answer a poll, and so there's always a chance error involved when we do something like that, and so we like to be able to measure that chance error, and so that's called the standard error. So here's how you measure the standard error. It's called the square root law. The standard error of the sum of draws is the square root of the number of draws times the SD of the box. I mean, this should make sense intuitively because the bigger the SD, which means that the bigger the spread of the numbers from the box, then the harder it is to predict the sum of the draws. So the bigger the standard error would be. In the same way, as the number of draws goes up, then the sum also gets to have a bigger range, and so therefore it'll be harder to predict the sum. And so that's why the error is based on both the number of draws and the SD of the box. However, as we pick more and more tickets, the error goes up not by the full factor of the number of draws that we make, but by only the square root of the number of draws. So that's why it's called the square root law. For example, if I pick 100 tickets versus picking one ticket, the error in the sum only goes up by a factor of 10 and not by a factor of 100. So the SE and the SD are different. The SD is a measure of the spread between numbers in the list, whereas the SE is for this chance process of trying to figure out the error that comes up when we randomly pick numbers. Okay, so let's look at this box. I think this is the first example we saw just at the beginning of the lecture, where we pick out 25 tickets from this box. And we found that the expected value of this sum is 75. And we want to know how big is the error is going to be. So the average of the box is 3. And so we need to find the SD of the box. And so again, this is back in one of the earlier chapter. We have to find the deviation from the average. Right, so the average was 3, so you have to find out all these numbers 0, 2, 3, 4, 6. How far is it away from 3? So those are the deviation from the average, and then we have to find the square. Remember, the SD of the box is the SD of a list of numbers is find the deviation from the average, and then find the RMS of that list. And so doing that, we get that the SD is 2. So now we can find using the square root law, we can find that the SE for the sum of 25 tickets is 5 times 2. And 5 is because of the. So 5 is because of the. Let's see this. So going back to this formula, we have the square root of the number of draws times the SD of the box. So we need those two points. And so because we're picking 25 tickets, the square root of 25 is 5, which is where we get the 5 from. And then the SD is 2. So 5 times 2 is 10. And so that means that the size of the error is about 10. So this kind of make sense of this. Let's suppose that I were to randomly pick 25 numbers from this list. So here's my list: 0, 2, 3, 4, 6. If I were to pick 25 random numbers from this list, we can write a program in Python or in any programming language we like to generate 25 random numbers from this list. So if I were to do that, I'd get something like this. And find the sum of this is turned out to be 71. So that means that we are 4 away from the expected value of 75. So the error is -4. If we do this again, we might get something like 76, for example. The error is about +1. Do this again, we might get 86, where the error is +11. If I keep repeating this over and over again, and do this 100 times, notice that here's a list of all the sum that we get. And when we look carefully at these numbers, we notice that they don't change very much. They have a very small range, even though in theory they could have a much bigger range. So for example, let's look at this problem. We want to know find the sum of the draws. We want to know the sum of the draw is likely to be around blank, give or take a blank or so. The expected value for this sum fills in the first blank, and then the SE fills in the second blank. And so, for example, 71 was one of the observed value for the sum. 76 was another one. If we look at this, 86, 78, etc. And so, in theory, as I said before, we can get the sum to be as small as 0 because What if we get everything to be 0? Or as large as 150, because what if I get, what if all my tickets was a 6? However, the answer we get is actually only from about 50 to 100, which is a very small range, considering the fact that we can get numbers from 0 to 150. So that says that when we actually do this out, the numbers that we get is within 2.5 away from the expected value, 2.5 SE from the expected value. So that's what we observed. The observed values are really more than 2 or 3 SE from the expected value. Okay, so let's look at another example. Suppose we're doing the same problem now. Again, picking 25 tickets from this box, but now we want to know what is the chance that we get observed values between the range of 50 to 100. Well, as we said earlier, if I pick 25 tickets, I could get 25 0, which give you a sum of 0, or 25 6s, which is give you a maximum sum of 150. So the question here is, what's the chance I get something between 50 and 100? And so we want to convert 50 and 100 to standard units. Again, this is from the normal distribution chapter earlier. And so seeing the expected value is 75, 50 is 2.5 SE away from 75, and 100 is 2 SE away from 75 on the right side. Again, converting these into standard units means that we. So for example, how do I get negative 2.5? It's 50 minus 75 divided by let's see. Let me kind of show you again here. This some of the value we saw earlier. So again, we want to convert to the standard units. So we have to know the SE of the problem, and as we calculated earlier, the SE that we found for this problem was, let's see, we found that the SE was 10 for this problem. So that means that when we get to when we convert it between 50 into standard units, we take 50 minus 75 divided by 10, which is negative 2.5. And then 100 minus 75 divided by 10 is 2.5. So that's how we convert each of the numbers into standard units. Now we use our Z table to find that the chance of being negative 2.5 SD on the left all the way to 2.5 SD to the right is about 99%. This is from the Z table. So that means that we have a 99% chance of getting a sum that is between 50 and 100. So notice, right, that it's really hard to get anything below a 50, and it's also very hard to get something above 100. So even though the range of possibilities from 0 to 150, 99% of the time we get a sum that is very that's in a much smaller range. Now, one of the problem about this formula is that finding SD is hard, and we need the SD in the formula, and so here's a shortcut for some problems where if the list of numbers we have has only two different numbers, a big one and a small one, and then those numbers can be repeated many times. So again, I have a list of numbers, but there's only two different numbers from this list. We call one of them big, one of them small, and so here's a shortcut for finding the SD of that list. Big minus small times the square root of the fraction of the big number times the fraction of the small number. So for example, 5, 1, 1, 1, 5, 1, 1, 1. 5 is a big number, 1 is a small number. 5 minus 1 times root of 1 over 4, which is a fraction of the big number, times 3 over 4, fraction of the small number. We get 1.73, which is a much easier way of finding the SD than actually using that method we saw from chapter 4. Okay, let's see how we can apply this to a problem. So say we play 10,000 times on a roulette wheel at a casino, and let's say that keep things simple, we're gonna put $1 on red. We want to find the chance that the house will win more than $250 from these plays. So remember that the house has the 20 out of 30 chance of winning in this game. So the problem asks for the chance that the house will win at least $250. So we have to find this probability of getting at least 250. So here's a box model. Remember, 20 tickets from the house perspective. 20 tickets will give the house a winning dollar, whereas the 18 tickets, where the person, the gambler, will win $1. So that means that the house has an advantage in this game. And so again, we use the find the expected value of how much the house will win per game. We find the average of the box. So adding up all the ones tickets and all the -1 ticket, divide by 38, we get that the average is 0.05. That means that on average, the house wins about 5 cents per game. And you play this over 10,000 games, the house expects to win about $500. Now to find the SE of the box, this is where we're going to use the shortcut formula for the SD. So the shortcut formula for the SD is big minus small times the fraction root of fraction of big times the fraction of small. So the big number is the $1, the small number is -$1 from the box model. So 1 minus -1 times the square root of these fractions give us approximately 1. So the SD is 1. So to find the SE, we use this formula, square root of the number of draws times SD of the box. So we get that we get $100. So that means that the house expects to win $500, give or take $100 or so. So now we can use the normal curve to convert this problem into a z-table problem. And so converting, because we know that 500 is the expected value, we want to know what's the chance that the house will win at least 250. We have to convert 250 into the standard units. So 250 minus 500 divided by the SD of 100 gives us that 250 corresponds to -2.5. And again using the z-table, the probability of getting the area to the right of the normal curve from the z-table of -2.5 is more than 99%. So that means that the house has a very high chance of winning at least $250 if this game is played over 10,000 times. So it seems like maybe this number is small, but when you think about it, a casino could have a lot of wheels, and then there could be a lot of people playing, and so over time, if you have a lot of wheels with people playing over and over again, and some of the bets might be more than $1, you see that the house has a big advantage to win a lot of money. So really, the house is expected to win about 5% of the money that's played, because on average, the casino wins about 5 cents for every $1 that's played. And then this square root law, the standard error, virtually guarantee that there's no risk to the casino. That's why the casino always win, and it's a really good business. And again, so let's look at an example where if you have a casino that has, say, 25 wheels, and we just assume that everyone plays with $1 just to be conservative and simple. Over 25 wheels, if every wheel they expect to win 250, every wheel they expect to win $500, and over 25 wheels they expect to win about $12,500. And if I were to find the standard error, we can find that the standard error only goes up by a factor of 5, because if we do this over 25 times, the standard error goes up by the square root of 25, which is 5. So that means that the standard error is now 500, and so that means that the casino is guaranteed about 95% of winning at least 11,000, because the error is only 500. 11,000 is 3 SE to the left of 12,500. So that means that the house is guaranteed to win at least 11,000. So to show you that, again, casino has a big advantage. So here's another example. What if I play the same game, except now we put $1 on a number instead of a color, and so it's hard to get to win with a number, and so they'll pay 35 to 1, and then the gambler has a 1 in 38 chance of winning. Again, there's 38 possible slots. So we want to know, what's the expected value of how much the gambler will win, and then the SE. So here's a box model. One ticket is $35. That's a winning ticket, and then 37 tickets is losing that $1. So the average is again 5 cents. We find the average of the box, and then you play 100 times. The expected gain is -$5. So that means the gambler will lose about $5 if they play this game 100 times. So to find the SE, we use the formula again. We need to find the SD of the box. So the SD of the box is 35 is the big number, -1 is a small number. Subtract them, times it by the square root of the fraction, give you about $5.76. So that means that, and then multiply by the square root of the number of time you play, gives you that the SE is $58. That means the gambler expects to lose about $5, give or take $58 or so. And so this is the reason why they like to play this game, is that the SE is $58. That means there's a big swing. You can win big or lose big, and so there's that's why the game is attractive, is that big swing. Suppose I have a die that's rolled 60 times. I want to find the total number of spots, the sum of all the spots, and then find the error. Also the number of 6 that I get, and also that error. So maybe, for example, if I roll this die 60 times, I might get the following die. I want to know what's the expected value of the sum of 60, rolling a die 60 times, and what is the expected time that I get 6. So if I count all the 6s, how many times do I expect to get 6? So those are the two problems. Part A is simple. That's basically just finding the sum of a draw from this box. So the average is 3.5. Multiply that by 60, we get 210. So we expect that the sum is 210. The SD of this box is 1.71. We can calculate that, and then the error would be square root of 60 times 1.71 based on that formula. So that gives us that the error is about 13. So if I pick 60 tickets from this box, I expect to get a sum of 210 where the error is about 13. Now to find the second part, if I pick 60 tickets from this box, I expect to get 10 of them to be a 6, because 1 out of 6 times we get a 6. So we expect 10 of them to be a 6. But to find the error of this is a little bit harder. Okay, so now the box again, we have to every time we do a problem, we have to look at the box the box model. So here's the new box model. All the tickets from 1 to 6. I want to know the number of times that I get a 6. So that means if I get a 1, 2, 3, 4, or 5, that's not getting a 6. So I put zeros for all those tickets. If I get a 6, then I count as getting a 6. So now our box model is 5 zeros and 1 1, because I only get 1 point for getting a 6. If I get anything else, I get a 0 point. Because we're trying to figure out the number of times that I get a 6. So with this new box model, the SD is about 0.37, as you can check using the shortcut formula, and then the SE is square root of the number of draw, which is square root of 60 times 0.37, so we get 3. That means if I pick 60 tickets, or if I roll a die 60 times, I expect to get about 10 6s, where the error is about 3, plus or minus 3. So kind of the recap here is that we might have these two problems that are slightly different. One of them is adding, finding the sum. The other one is counting and classifying, but they're done the same way. That's kind of the key point of this, is that if we classify or count, we put zeros and ones, because 0 for something that's not part of the count, and 1 if something is part of the count. And then so the two problems is kind of summarized by this picture. If I want to find the sum of the draw, the box is all the numbers. If I want to count the number of times something occurs, we put the box is now zeros and 1, where 0 is not part of the count, and 1 if it is part of the count. So in that example, when we counted the number of times 6 appear, everything else is 0 because that's not counting, that's not contributing to the count, whereas the 6 contribute a 1 to the count. So one last example here. What if I toss a coin 100 times? We want to find the expected value and the standard error for the number of heads, and we'll find the chance I get between 40 and 60 heads. So here's a box model, right? Because we're counting, that means the box model is a model of zeros and ones, and because a coin can either be a heads or tail, if we get a head, we have a count of 1. If we get a tail, we get a count of 0. And so that's the box model is 0 and 1. So 0 for tail and 1 for head. So we get a 50% chance of getting a head. And so again, applying our formula, we find that the STE for the sum of the 100 draws from this box is 5. And so that means that if I toss a coin 100 times, I expect to get about 50 heads, give or take 5 or so, where 5 is the SE. So what's the probability that I get between 40 and 60 heads? Well, let's look at notice that between 40 and 60 is actually 2 SE away from the expected value of 50, right? Because the expected value of 50 and the standard error is 5. That means 40 is 2 SE on the left of 50, and 60 is 2 SE to the right of 50. So using the Z table, we can find that the chance of the probability of getting something between -2 SD and +2 SD is about 95%. So that means that if I toss a coin 100 times, I expect to get I expect that 95% of the time I get between 40 heads and 60 heads. And notice that's not too surprising, because likely we get on average about 50 heads, and so that means that most of the time we get between 40 to 60 because the standard error is about 5. And so that means that it's very unlikely if I toss a coin 100 times to get all heads, right, or all tails. So that's very unlikely. But to get between 40 and 60 is very likely, around 95% of the time. Okay, thank you very much.